Good morning or good evening. Thank first Pedram and Giovanni for the invitation and giving me the opportunity to, at least in a virtual setting, contribute to what we're doing recently in this field. But honestly, I'm really looking forward to go back to the more face-to-face meeting. This is it's challenging, and of course we've been all now Zoom experts over the last year, but I don't want to learn, as Eric just said, after here, I think we get a little tired with this. Anyway, thanks so much for the invitation. So what I'm going to talk about are two connected and I would say really new topics that we are really interested in. And I have to say, even over the last year, we've made some real nice progress by even remote doing experiments in Alba in Spain at the synchrotron. And of course, students sitting at home and analyzing the data. It was challenging, but I think, and I hope you will agree with this, we came up with some very nice results. And this is, I'm going to share with you. So this is about using X-rays to image not only topological spin textures, but also most recently, geometry-induced three-dimensional spin textures, which I find is a very interesting new directions. Okay. So that's, of course, the daily view that you have, if you're in Berkeley. The weather's nice, and the view is great as well. And if you come by, hopefully soon again, I'm more than happy to host all of you. I also would like to acknowledge at this point that the work that I am doing in my research is funded by the Department of Energy. Okay, so outline is very simple. I have two topics. The first one is about novel topological spin textures, and here I want to share with you our latest results where we looked into Hopfield structures, which we haven't talked about so much in this session here. But I think it's a new direction that I hope will create a lot of excitement in the community, both from many aspects. And then a second part of my talk will be about geometry-induced spin textures. Again, this is about take a film and basically put them in a curvature on a curved surface. And we saw some very interesting recent results related to that. But before I start, I definitely want to give a high acknowledgments and a shout out to all these people that helped me to do this work. And I want to particularly mention here Robert Streubel, my previous postdoc. He now moved on and he's now at the University of Nebraska in Lincoln. Noah Kent, my former student, had to leave during the pandemic. There was of course no farewell party, nothing like this. It just turned the keys in and that was it. He's now at UC Boulder. And then my new student, David Raftery, he joined just before the pandemic, hasn't been to the lab at all. He's sitting all by himself at home. Again, we're all really looking forward and, moving into the more brighter future very soon. And then a couple of people, Charles-Henri Lambert, now at the ETH in Zurich, and Neil Reynolds, they made multi-layers for the work I'm going to present here. I always like to acknowledge people at the Foundry, where we are doing most of our nanofabrication. Sujay Roy, my long-term collaborator, together with Steve Cavan and James Lee, about all scattering experiments that's happening at the ELS. Paul Sutcliffe, I want to really emphasize here, he was the theorist in the background, a very strong collaboration who helped us really understand our Hopfield images that I will share with you in the next couple of slides. And then I just want to say the collaboration that we just recently started with the group at Alba, it's just fantastic. And I really appreciate Lucia, I think she's in the audience here, Andrea, Eva, and Salvador. And then, a shout out absolutely to Aurelio, who was instrumental in helping us with both the Hopfield as well as the geometry-induced one. And Elizabeth Justin and the team from Jülich and Helmut Center in Berlin were critical for making the samples that I'm going to share with you. So that was a long introduction. Very briefly, what we're really interested is identifying and discovering new magnetic materials, because as we all know, magnetic materials are so dominant in our life. And we have to find new ways that not only are economically viable, but also environmentally friendly, as well as, of course, low energy and all this. And I think the key is not to stick anymore with the pure charge that we used to use every day in electronics. This is about really exploiting the spin to the largest extent possible. We all know this. I'm speaking to the choir here. Spintronics, where we use the spin degree of freedom, and in the end we need to find ways to really deal with the spin currents ultimately. So as we all know, and this is just again talking to experts here, spin textures at the end are the foundation. So if you want to discover new materials, you have to understand the spin textures, and there's of course these two kind of principal kind of alignments or spin arrangements that the spin take on to go into the ground state. One is, of course, this collinear spin texture, a collinear interaction that is given by the Heisenberg exchange interaction. It leads, of course, to ferromagnets, antiferromagnets, ferrimagnets, and then, as Eric just pointed out nicely as well, there's then the non-collinear asymmetric, anisymmetric exchange coupling, the Jalashinsky-Murray interaction, and you play with those two interactions in one way or another. You can discover novel materials by tuning those two interactions, and this is, as we just heard in the previous talks, broken inversion symmetry, in particular the interfaces. And this is, in the end, I think, our toy, our playground that we're really excited about. Okay, so now we come to the topology, and of course, the topological spin textures have, as we just heard in the past talks, a lot of excitement, a lot of activities going on. And I feel we're seeing right now, we're witnessing this transition when we go from a two-dimensional topological spin textures more towards the real 3D spin textures. And just look back like 15, 20 years ago now, yes, almost more than that. I mean, we started looking into vortices. Vortices probably that was the simplest topological spin texture that we could think back then, using permalloy as a prototype magnetic materials, and then just carve out a little nano disk, and then just watch those interesting spin textures, as you all know, characterized by an in-plane circulating spin texture. And then when it comes closer to the center, of course, this doesn't like this kind of smaller circles anymore. It pulls it out of the plane. And we have now these 2 degrees of freedom to play with. One is the polarity that can be in the vortex core up and down, or the chirality, I would call it circularity because it goes in a circle, that is basically going clockwise or counterclockwise. So, and then we moved on the community going into the skyrmions. And when you compare now, going back to the vortices, what is a vortex compared in terms of topology? Basically, you make a half turn from left to right. You go from, pointing towards you, against you, that's the half turn, that's called a half skyrmion. But the skyrmion really brought us this idea about topological skyrmion numbers, the winding numbers, as has been already discussed in the meeting today as well at many times. So this is really what makes it exciting. It's this kind of topological protection that you heard about, and it's the characterization is really this winding numbers as described here. So you go from the left side of this skyrmion texture pointing up, and then it goes to in the center pointing down the mechanization and pointing up again on the other side. And of course, there are these various skyrmions, block type, nail type, and so on and so forth. What is the next step? So let's assume we're done with the skyrmions. What comes next? And I think, and I mean, this is also something, and I saw even Stavros in the audience. I think there's a lot of people that looked into this really a long time ago, where they said, okay, we need to probably go into the third dimension. And there's not only then just one topological numbers, there's a second one. And this Hopfields schematics that's shown here that I took from Philip Rybakov, that's posted in archive, actually shows exactly what this is about. So what you see here, this is an iso surface with the colored lines, basically resembling the mechanization of spins pointing in one direction. But then what they do is they not only just rotate, like they have the winding number, but there's also then a kind of a twisting. That means you basically you see the iso lines going in a kind of a twisted state around this. And this, in the end, is now the next kind of dimension that I call to be interesting to look at. And I think there's just no way, and if anybody in the audience can correct me, but I think this really requires to be in the third dimension, because you cannot do this kind of winding and twisting just in a lower dimension. It's just not possible. And this, again, what is, of course, in the Hopf number, that's the kind of analog to this. It's the linking number. It's being described at the bottom. Basically, it's kind of this linking of structures, not topology, that also comes into play. And it started probably by mathematical concepts, but now we're going into, can we realize them in real magnetic materials? Okay, now this is also kind of accompanied, I would say, from people start looking from the two-dimensional skyrmions to the three-dimensional skyrmions. And here's just 2 examples. Actually, can I get a pointer somewhere? Where the group from Jülich found experimental evidence for the so-called chiral boppers, which of course is it starts with a skyrmion tube that goes through the thickness of the sample, but then actually by applying a certain field sequence or various parameters, you basically squeeze it or you confine it to a so-called chiral bopper with a block point at the very bottom here. And this, I think, is of course an interesting new spin texture that again requires the third dimension. And what they've shown here in this paper is that you can encode and very easily I mean, the ones and the zeros. So instead of just having a skirmion racetrack where you basically have the skirmion on or off, here you can really encode a little bit more information to this. And I think this is an exciting new direction to go into. It has a lot of interesting science, particularly due to the block point here. The dynamics, I think we haven't even yet started looking into this. But that's clearly very interesting. At the same time, skirmion strings, I think it's another three-dimensional spin texture that's just emerging as we speak. And that gets a lot of interesting attention from the community. And this is just a paper from Seki, where he looked into propagation dynamics of spin excitation along the skirmion strings. And here's just, I think it's simulations mostly, where you see very interesting, modes that are happening in this kind of three-dimensional skirmion textures. Okay, so we were actually stimulated a little bit by this Hopfields. We said, how can we make those Hopfields? Can we really realize, Hopfields from what we know? And we started off by basically going back to a paper that, was, published by Bogdanov and Huot, many years ago, where they described the so-called n-pi vortices, which is then, of course, not just, as you see here, the skirmion, which has only one rotation when you go from the left corner to the right one, but these are multiple rotations of the magnetization. And these are called target skirmions these days, just come up with a name. I think probably because at the end it looks like a target symbol, right? And so these are now, these are simulations here that would show you that you have two kind of rotations. You would have the skirmionium that people have looked into, and then of course you can extend this to multiple rotations, 3-pi, and so on and so forth. And the way we tried to approach this from an experimental point of view, we said, okay, how can we actually make those? And we used the so-called imprinting of spin textures in magnetic films. So we basically coupled two of our expertise together. We said, let's take a vortex structure that we know and have studied for quite a while, as many others, and bring them in proximity to a PMA material that shows, of course, a skirmion texture. This was the regular iridium cobalt platinum multilayers, and we just put them on top of each other. That was the synthesis approach. And when they said, okay, what happens then to the spin texture underneath this vortex structure? You have this in-plane circulating one and bring it on top of the PMA material with the skirmion texture. And well, what we found is, and then we used, of course, the X-ray microscopy to look through the permalloy disk because of the penetration power, and we had the elemental specificity, and we looked through the permalloy disk just underneath the disk and watched basically the spin texture that was emerging, and it was finally imprinted due to this interaction in the platinum cobalt iridium system. And here's the result. We saw a couple of interesting spin textures, and we identified them to be target skirmions with varying rotation of the magnetization. And here's the example for one rotation, and you have to look for closed kind of spin kind of rings, the concentric rings. And here we said, okay, there's the main skirmion right in the center, surrounded by, of course, the first rotation. This was the n=1 target skirmion. Here you see an n=2 target skirmion, and here you see n=3 and 4, and so on and so forth. So we finally had to stop because I think there was a certain diameter of the permanent disk, and we couldn't fit more of those into this. What was interesting is that the target, the topological number, the skirmion number, basically was just toggling between 1 and 0. So it was not really, something that would just expand. There was one thing, and when we looked also into stability of those by applying a certain field sequence, we realized that in the end, the stability is given more or less by the central skirmion, and that's it. But anyway, why was it even interesting then to look into this, let's call them higher order target skirmions? This is because when we talked to Paul Sutcliffe, and he had a paper out there, he said, well, target skirmions could probably be the precursors for Hopfields. And we said, that's great. We know how to make target skirmions. Now let's move on and try to identify Hopfields. And let me just show you briefly how those target skirmions would look different from a Hopfield. And this is now schematics again showing you that the target skirmions that you just saw, basically the two-dimensional projection of this, looks very uniform across the thickness of the disk of the layer, right? So it's all black on this side, purple here, white, yellow, and so on and so forth. Now, what is different compared to Hopfield is that right here at the top layers at the surface, you see this deviation from the target skirmion feature. So this is a characteristic, and when you look closer into this feature here, this is kind of a skirmion pattern structure, a spin texture that has, of course, that goes like this torus around here. So for us to address this now experimentally, it was pretty clear. What we need to do is to distinguish target experiments from the Hopfions. We need to find ways to image these systems all the way throughout the whole volume. I mean, basically going through, and particular pay attention to this top layer, because this is where it looks like, you know, the vast majority is changing here. So if you can compare our systems from the target experiment and the Hopfions, we should see very clear signatures that are characteristic, particularly at the top here. And this is actually what we did. So we used then a combination of two X-ray microscopies that has been established. There was nothing new to develop anymore. We used the surface sensitivity of X-beam. So we actually put the sample in the so-called X-ray photo emission electron microscope, where you see basically the first couple of nanometers, the spin texture. That's just the way how they're being detected by these photoelectrons. They escape a certain surface layer only. We used for both of them, of course, the same XMCD contrast. That was clear. That was the elemental specificity for that. And then we used also the same samples, the identical samples. We had a marker, and we knew exactly this was our little disk that we just looked at with the beam. We put them in a full field microscope. We looked all the way through, and we were able to see both the top layer as well as the bulk sensitive spin texture that's coming through. Spatial resolution was for both of them about the same. Should be significant and large enough to distinguish those spin textures that we were interested in. Okay, and then of course we went back again to Paul Sutcliffe and say, Paul, can you tell us a little bit how should we design now the PMA profile across the thickness? And he gave us some numbers. We ended up with synthesizing various systems, and what you see the difference is that this designing of the PMA profile, that was the key to basically transform from a target skyrmion to the Hopfion, was the thickness of the cobalt layer that was sandwiched in between a platinum and an iridium layer, and we had a couple of repeats of them. What we see here for the Hopfion system down here, this 1.5 cobalt nanometer layer was just reduced slightly to the 1 nanometer layer, and it was this kind of designing the PMA across the thickness that should, at least this was a prediction from theory, allow us to generate and create Hopfions in these multi-layered systems. And then we also did some, expectations, characterization. How would a PEM system, a PEM image look different for the target experiments versus the target experiments versus Hopfions? And it's pretty clear these are simulated experimental data for the full field transmission bulk sensitive one, the MTXM, and this would be for the PEM. For the target experiments, would look very similar. Again, this just means, yes, it goes all the way through. Doesn't make a difference whether you look at the surface or the bottom. Whereas for the Hopfion, which has the characteristic surface kind of changes of the spin texture, this would look completely different. So it's very clear. If you see something that looks more like this, you know it's a target experiment. If you see something that looks like more like this, you know that's a strong indicator we have a Hopfion. And here are now then the experimental data that we were able to do. And this was again the combination between an XPEM instrument that we used at DLS, and we went to ALBA to the Mistral beamline and did the full field microscopy images. And then this were again simulations. Now we did also a rotation, a kind of an angular dependence of the PEMs, the structures, because we want to really be very clear that we reconstruct fully in 3D at least the surface layer. This was very critical because this is where we knew there was the majority of the differences, and make sure that this is really Hopfion. And then the MTXM, again, this for the experimental data looks very similar as expected, but also the PEM was very significantly distinguished to be a Hopfion structure. Just to give you a couple of ideas that it could not be anything else. I mean, the target schema we excluded it very clearly, but also torons, which is another kind of a three-dimensional spin texture. Just compare, this is the Hopfion PEM image, that's the toron. There's no way that you can even say this will be the same. So it was pretty clear for us that we have seen these Hopfions in these multi-layers. So not only we designed them to be like this, we had a very clear experimental proof as well. So it all came nicely together. We saw it now statically. Of course, what's the next step to do? And it's just a little outlook. What is interesting about Hopfions compared to skyrmions? I think the big difference is, Anne Bratish, I think, mentions in his paper down here, no Xiaodong Zhang. The Hopfions have no net gyro vector. That means they have no deflection. So that means if you send them on a racetrack, skyrmions versus Hopfions, I would assume that the Hopfions have a clear advantage because they just go straight. They're not being deflected by kind of a Hall effect. And this is something that we are now, of course, pandemic has slowed us down a little bit in this direction. But we want to do, of course, as the next step, look into some, Hopfion dynamic experiments that we've done in the vortices that we've done with the skyrmions. And it's a natural thing to do. so we're really looking forward to that. We can go back to the lab and make those samples and then, you know, put them in the beam and start doing this. That's clearly the next thing to do. Okay, so this was so much about novel topological spin textures in 3D, discovering and observing these Hopfields. And now let me switch to my second topic. How many minutes do I have? 5?
You have about 5 minutes, yeah.
Okay, great. So again, going into next dimension magnetism, the 3-dimensional one I just mentioned to you has also, of course, a geometrical aspect to this. And this is, I mean, there's just a little cartoonish here that so far we looked mostly in 2-dimensional system, but what if you just basically start looking into a Möbius band, start looking into, you know, a core shell structure and things like that. This opens up opportunities for synthesis, characterization, modeling with new physics and new applications. And people have looked into what is now the geometry is basically maybe summarized under the curvilinear magnetism results. And here's just a few examples what people have done so far. And there's just a flurry of papers posted every week on arXiv right now that shows you how important it is to look into the geometry. Let me say one thing why I think it's really interesting to look into this. And I mean, on a flat surface DMI and an exchange interaction, we know exactly what it looks like. But just imagine a ferromagnetic system that is exchange coupling, simple Heisenberg parallel, we heard it in the previous talks, put them on a curved surface and neighboring spins will probably start to bend, which means it looks like if there was a DMI effect to this, right? So it's a geometry-induced modification of a DMI. And this, I think, has effect to the spin texture. There's another paper that was just published recently from, I think, Wessler is also in the audience, where they've indicated that the domain wall should have a different feature, and in particular should be an inclination angle to a nano, to the axis of a nanotube. And that was something that, well, we looked into this, started looking at this. So we made basically a multi-layer nanotube and wrapped it around a carbon nanowire that's shown schematically here. This was done by Elizabeth Joosten and the Jülich team. A regular permalloy PMA material that is well known, but wrap it around a non-magnetic core, generate a nanotube, and watch the domain walls there. And this is an SEM image shown down here. We went again to Alba Mistral, did full 3D tomography of this, and I think Lucia is also and Aurelio in the audience. We did almost a full scan, a little bit in the angular range, and watched then the domain structures in this curved nanotube, in the multi-layer that's curved and wrapped around a nanowire nanotube. And here just raw images showing you that we did see magnetic contrast between the L3 and the L2 edge. And interestingly, and don't ask me why this happened, our system, maybe due to the deposition, showed up with 2 vortex structures on one end that happened to be in opposite direction, which means the system was forced to undergo a domain wall transition in between. And what this is now, let me show you the results. This is the fully reconstructed 3-dimensional spin textures of this curved the nanotube that was wrapped around the nanowire. And what you see here is there's a vortex configuration pointing clockwise on the right edge and counterclockwise on the left edge. It means in the middle here, somewhere, this needs to basically switch its chirality. And what we've seen is this domain wall was not what you would have expected probably on a straight film would be orthogonal to the axis. It came out at an angle. And this was exactly what, you know, this paper from Uli Rössler and others have predicted. There should be an angle. We measured the angle and then did some simulations to show where we end up and how is the DMI affected by this. This is the data point here for 150 nanometer diameter of this nanotube. We were very consistent with the and you can see it here in the simulation, no DMI, which have a straight domain wall here. With the DMI, of course, there's this, and the stronger this DMI would be, the larger the angle would be. And we observed, of course, a certain value. That means we could trace back again what was the geometry-induced DMI modification to the system here by just watching the angle that's of the domain wall relative to the axis of the nanowire. Okay, with that, let me summarize here briefly. I hope I could give you a glimpse into how really magnetic X-ray spectrum microscopy allows in a unique way to study properties, behavior, and function of these novel topological spin textures. I'm so excited, and I hope my whole team is also excited. Null spin textures will emerge when you go finally into the 3rd dimension. And it's not going back to bulk system, it's going into designing, you know, with feed bit and other techniques to, you know, design a material that nature just doesn't give us. Challenges for synthesis, characterization, simulation. The Hopfields, we were really very excited about, driven by the theoretical predictions, and then finally we're able to use with this combination of different techniques and characterize the 3D textures. Ultra fast, ultra small. We have some other results from LCLS I'm not going to share today. The 2-pulse XPS, where we found really interesting ultra fast spin fluctuation. And finally, curvature, I think, is our new toy to play with. It's a new design parameter that I believe impacts the spin textures and therefore properties of normal magnetic materials. Thank you. That's all I have to say. Thank you.